Hi everyone, this is Hal Tasaki. In this online lecture, I'd like to discuss the main results of my recent paper with this title. And actually, there are two videos for this single paper, and now you are watching the longer version. So if you are an expert and would like to quickly see what's new in this paper, please go to the short version, in which I only discuss the essence. So this longer version contains some details as well as a pedagogical introduction to the topological phase transition in the SSH model, which I believe to be useful if you are not an expert. Okay, anyway, let's get started. So as for non-interacting topological insulators, we know a lot. This famous periodic table and many rigorous index theorems. But as for interacting topological insulators, even though there are a lot of works, and I'm sure that I'm missing a lot, complete classification is not yet known. There are mathematically rigorous works, but they are still limited. In this paper, I presented a new rigorous index theory for a class of one-dimensional topological insulators, including the famous SSH model. And this theory establishes the existence of a symmetry-protected topological phase transition in the infinite system, and also the existence of gapless edge mode. Okay, but I claim that the proof of our theorem is very elementary and simple. No functional analysis, no operator algebraic technique, no nothing. Okay, right. So before going into my work, as I promised, I start from introduction, a quick review about topological phase transition in the SSH model, Schrieffer-Heeger model. So I consider a one-dimensional system of spinless fermions and denote by C dog R, C, and the standard creation annihilation number operators at site J. J takes the integer value, and they satisfy this anti-commutation relation. SSH model is a system of non-interacting fermions at half filling with this Hamiltonian. It's a very simple Hamiltonian with nearest neighbor hopping, but this hopping amplitude sort of alternates like this. Okay, S is a parameter that takes value between 0 and 1. And here, this is just an interpretation, but we interpret that sites 2j and 2j plus 1 forms a unit cell. So in this case, 0 and 1, this is a unit cell, this is a unit cell. This is just an interpretation, but this will be important for us. Okay, so let's start by examining the two extreme cases, that is S equals 0 and S equals 1. For S equals 0, the SSH Hamiltonian is simply this. So there's hopping between 2j and 2j plus 1. And in this case, you can easily write down the ground state at half filling, that is this. Okay, this is a state without any particles. And this operator creates one particle within a unit cell. So it's jumping between this and this. Okay. Actually, this is an anti-bonding state with minus sign, but don't worry, because it's just a sign convention. If you put minus here, then this becomes a usual bonding state. Okay, so this is a picture. So within each unit cell, you have this kind of bond. And for S equal 1, it's basically the same thing, but now you have bond that is connecting neighboring unit cells like this. This is the state. And so they are basically the same thing, but people call this trivial state, this non-trivial state, because so this depends on the interpretation of unit cells. So in this case, each bond is confined within a unit cell, but in this case, a bond connects neighboring unit cells. So that's why people call this trivial or non-trivial. Or if you consider the corresponding system on the half-infinite chain, and then in this S equals 0 case, yeah, this is the ground state. There's nothing to worry about. But when S equals 1, there is one site on which you don't know what to do. Okay, so this is kind of non-trivial. And in this case, we have gapless edge mode here. Okay, so this is just for S equals 0 and 1. What happens in between? So to see this, I consider a single particle Schrödinger equation for the chain with two L sites with periodic boundary condition. So this is the general single particle state. Vacuum creation, so this creates a particle at J, and this is coefficient, complex coefficient. And so this is the Schrödinger equation, and this is the Hamiltonian. If you plug this Hamiltonian in here and do a little bit of computation, you get a more familiar single particle Schrödinger equation. So phi is the wave function and E is the energy eigenvalue. Okay. Now, since we have translation invariance, we can assume the Bloch wave function where this is e to the ikj, the plane wave part. K, of course, is a wave number. And U0 and U1 are some unknown, but unknown quantities. Okay, and if you plug this into this Schrödinger equation, then you get this. So this is basically the Schrödinger equation for this system. And so this is nothing but the eigenvalue problem of this 2x2 matrix. Okay, and of course, this is very easy. This is just a freshman linear algebra. And you get energy eigenvalues like this. So it's parameterized by plus minus. This is called the band index and K the Webb number. And it's like this. So see that this is invariant when you change S to 1 minus S. Okay, here are the plots. So when S equals 0 or 1, you have two dispersive bonds. This is E minus, this is E plus. And so two dispersionless bands separated by a band gap. So this represents a general situation when S is larger than 0. So S is not 0 or 1 and not 1/2. Then you have two dispersive bands separated by a band gap. And only at S equal 1/2, the two bands touch. And you don't have any band gap here. So this is just for one particle. So we want to look at many particle ground state at half filling. Then this is, of course, very easy, as you learned in school or as you teach in school. You only need to fill the lower band like this. Okay, and then you find that in these cases, there is a band gap in this many-body ground state, because in order to excite this, you have to move this. For example, move this particle to here, then you have to pay some energy. But only in this case, it's gapless. So to summarize, the model has a unique gap ground state except at S equal 1/2. And by a unique gapped ground state, I mean a unique ground state accompanied by a non-zero energy gap. I will make this abbreviation repeatedly in this lecture. Okay. So this is our phase diagram. Okay, this is trivial phase, non-trivial phase, separated by a critical point, gapless point. But if this is a phase transition, but this phase transition cannot be characterized by an order parameter because there is no symmetry breaking. Here you have unique gap ground states. Here also you have unique gap ground states, no symmetry breaking. So this may be characterized only in terms of a topological index. Okay, to find a proper topological index, we look at the Schrödinger equation. And so the key player is this 2x2 matrix. So let me write it in this form. Here are the two Pauli matrices. So you see that this real part of alpha k and the imaginary part of alpha k is something. So let us look at the trajectory of this point in 2 dimensions when k runs from 0 to 2 pi. Okay. So here's the plot, and now you see something topological. If you look at the winding number around the origin, as k goes from 0 to 2 pi, and like in this case, it doesn't go around at all. And here, the winding number is not well defined because the trajectory touches the origin. And here, clearly, the trajectory goes around the origin once. Okay, so if you look at the winding number, it's well defined except at the critical point. And it takes value 0 throughout this trivial phase, and it takes value 1 throughout this non-trivial phase. Very nice. So this winding number characterizes these two phases. In equation W, the winding number can be written like this, where theta is this phase factor angle here when you express this alpha k in this polar form. But we have to admit that this way of defining topological index is rather ad hoc. So let me look at a better description, and that is called the Zach phase. So we want to have this, we want to compute this winding number. So we need this theta. Well, for this purpose, let's look at the single particle energy eigenstate corresponding to this energy eigenvalue. Then you easily find that it's written like this with this u plus minus k. This is the eigenvector of that 2 by 2 matrix. And if you, again, this is freshman linear algebra, and you find that this eigenvector is written like this. And here, look, we do have this phase. So in order to pull out this theta prime, you only need to differentiate u plus or u minus. So for example, u minus with respect to k, and then minus I theta prime appears in front. And so you don't need this. So you take the inner product with this same thing, and then this guy disappear, and you're left with this. Very nice. So we see we have theta prime. We can write theta prime in terms of just u minus k, the eigenvector or the wave function. So if you put it into this integral, then we get this thing, which is usually called the Zach phase. Actually, we divided this by pi to make it 0 and 1. This is not standard. Usually, you don't have this pi anyway, but this is called the Zach phase. And if you're familiar with the Berry phase, yes, this is nothing but the Berry phase where k, where the parameter is replaced by this wave number k. Okay, that's called the Zach phase usually. And so anyway, we have this well-defined Zach phase written in terms of a wave function, and this takes value 0 or 1, depending on which phase you are. Okay. Actually, here I cheated a little bit. The winding number can take any integer value, but unlike W, the Zach phase nu is defined only only mod 2. That is because you can make a gauge transformation for this wave function. But anyway, this is what you get. And this is what is important. Okay, so that's nice, but I want to express Zach phase in a more useful way, a way which is useful for me. And that is that this is nu is a Zach phase, but I claim, oh, of course, everything is standard. This is review, but I claim that the Zach phase nu can be written in terms of an expectation value in the many-body ground state, okay, like this. Okay, what are these? First of all, phi ground state is this, okay. This is the ground state of this free fermion system. So this has this Slater determinant form. It's very simple. A k is the creation operator of the single particle energy eigenstate correspond with this energy. Okay, you just use this eigenvector u minus here. And u twist, this is something new. And this is a twist operator or the flux insertion operator introduced by Bloch. The same Bloch, but different work long time ago, and also by Lieb, Schultz, Mattis in their very famous paper in 1961. And this is basically the U1 rotation. Okay, but the rotation angle here depends on site. So it's 2 pi j over L. So it's basically start with 0 and gradually increases and finally goes back to 2 pi. It's the same as 0. Okay. Now also I'm going to show this relation, show this equality. So these are what I already explained. So let me compute this thing. Now, so I want to apply this operator to this. And then this is just an easy fermion computation. And you find that the only effect is that A changes to B. A dagger changes to B dagger. What's B dagger? It's basically like A, but this here, you have a shift in this wave number. And this shift delta k is, of course, 2 pi over L. It comes from here, okay? And nothing else changes, okay? Now, I compute the anti-commutation relation between AK and B dagger k prime to find from this Fourier part that it's non-zero only when k and k prime plus delta k is equal, okay? And this is the coefficient. Now, so this means that k and k prime must be very close with each other. So you can Taylor expand this here to get this expression. And now we have something we want. Okay, I continue the computation. So I want to consider this expectation value. So this is what we get. And then here we have some sign factor, but this precisely cancels with fermion sign, and you get this. And I plug in the formula for expression for this anti-commutator like this. And then, change this to exponential and, change this to sum and to integral. Everything is very simple calculation. And finally, you get this. And this is the precise integral that we used to define this ZAC phase. Very nice. So we have shown that this expectation value of the twist operator in the infinite volume limit is exactly equal to e to the I pi nu, where nu is the ZAC phase, which is either 0 or 1. So this expectation value is either 1 or minus 1. Okay, and so this distinguishes between this phase and this phase. Okay, so this will be useful for our main part, for the main part of this lecture. Okay, so before going on, I will make a remark about the role of symmetry. Consider a model without something called sublattice symmetry, that is a Rice-Meller model. And this is obtained by adding this staggered on-site potential to the SSH model. And then you can easily show that this model has unique gapped ground state, except at a single critical point where s equals 1/2 and u equals 0, the SSH critical point. Otherwise, it always has a unique gapped ground state. This means that within this phase space, H0 SSH and H1 SSH belong to the same phase. That means you can go from here to here without passing through any singularity, any critical point. So, but I said that they belong to the different phase, belong to different phases. That was because there was a symmetry. So if we only consider a model with sublattice symmetry, that is considering only the u equals 0 case, then there are two definite phases in this problem. So that's why these phases are called symmetry protected topological phases. You need symmetry to protect this phase structure. Okay. So in the rest of this lecture, I will consider only models which have nice symmetry. Okay. And one more remark: what happens to the ZAC phase? Actually, the ZAC phase or the Berry phase in general are not quantized like in the unlike for the case for the famous Chern number. Okay, and but if you define nu plus minus like this, so I define ZAC phases for the upper bound and lower bound. And then in this case of general two-band models, including this one, you can show that the sum of two ZAC phases is 0, not 2. So that's all you have in general, like in this model. But if the two bands are symmetric, as in the case for SSH model with u equals 0, then you have additional equation nu plus equal nu minus. And then this and this means that nu should be quantized to 0 or 1. So that is what's happening for the SSH model. Okay, so that's all for the review part. So, and let me go to the main part of this lecture. So I will first define the class of models that we consider. So we consider interacting and possibly disordered model of spinless fermions at half filling with this general Hamiltonian. Okay, this TJK is the hopping amplitude, which I take to be symmetric and real. And I assume that this is hopping is 0 if j minus k is even, which means you can have hopping between 0 and 1 or 0 and 3, but there's no hopping between 0 and 2. Okay, and I also assume that it's short ranged. R0 is some constant, and it's summable like this. T0 is some constant. And interaction, as for interaction, I assume this form. But otherwise, V is essentially arbitrary. It's symmetric, real, of course, and it's short-ranged and bounded. Okay. And the important thing is that this general class of Hamiltonians include the SSH Hamiltonians. So, of course, both SSH0 and SSH1 are in this class. And here's an important corollary of our main theorem. We claim and we prove that this H0 SSH and H1 SSH belong to different phases within this class of models. So this is a very rough picture. This is a huge space consisting of all these Hamiltonians. And here's the SSH model. I claim that there's something in between them. More precisely, let HS be any path of Hamiltonians in this class, of course, such that H0 is H0 SSH and H1 is H1 SSH. then I prove that HS must go through a phase transition point with either non-unique ground state, gapless ground state, or discontinuity. So we don't know what's there, but we are sure that from going from here to here, you have to go through something. And this we prove rigorously in an elementary manner. Okay, so here's some words about strategy of the proof. So I note that the model has no translation invariance. I don't assume any translation invariance, so no band structure. Oh, the model has interactions. So the ground state is not a simple Slater determinant. You can, in general, you cannot write down a ground state. Ground state is an intractable many-body state. And we shall study phase transition rigorously. That means that we must treat infinite systems. So this means it looks like the business is very, very difficult. But this is our strategy. We define a Z2 valued index in terms of the sign of the expectation value of the local twist operator in a unique gap ground state on the infinite system. So we only use the expectation value. That makes our proof, our theory, very elementary. Okay. Now here's a remark about the symmetry. I already stressed the importance of symmetry, and this model has a very nice symmetry. First of all, particle number is conserved. So we do have standard U1 symmetry, quantum mechanical U1 symmetry. And also, I claim that this model is invariant under particle Hall transformation followed by a gauge transformation on one of the sublattices. This transformation is described by this map gamma, which mathematicians call linear star automorphism. That's something, this is standard, satisfying this. And in this case, gamma is defined by this. So Cj is transformed into this. So annihilation operator changes to creation operator, and also you get extra -1 factor if you are on an odd site, Okay. And so this is basically particle fold transformation. So n changes to 1 minus n. And okay, so I have made some restriction on this t, and that was chosen. That assumption was made only to make this hopping part invariant under this transformation. And also this, look, this n-1/2 form, this form is invariant under particle Hall transformation, this. So we see that this Hamiltonian is invariant under gamma. Okay, that's the symmetry. And by omega, I denote the ground state of the infinite chain. And I'm going to give a precise, mathematically rigorous definition of a ground state of the infinite system later in this talk. But for the moment, you can safely assume that this omega A denotes the expectation value of any local operator A in the infinite volume limit of this ground state expectation value. Okay, so phi ground state L is the ground state on a finite chain with suitable boundary conditions. So this is a finite volume expectation value, and you take infinite volume limit. Okay, and when ground state is unique, then it must have the same symmetry as the Hamiltonian, so it must be gamma invariant. And gamma invariance means that for any local operator A, the expectation value of gamma A is the same as the expectation value of A. Okay, that's the symmetry. And now I will define our index. For this purpose, I introduce twist operator. And first of all, by a theta function, I mean a function from R to S1. I parameterize S1 like this. And this theta type is 0, always 0 when x is less than or equal to x0. And it's always 2 pi when x is larger than x1. And x1 and x0 are separated roughly by distance L. And I also assume that theta changes only slowly, gradually. So the gradient of theta is bounded from above by a constant gamma. And I finally assume, this is important, theta wraps around the circle S1 once in the positive direction as x changes from x0 to x1. Okay, by using this theta function, I define local twist operator following the philosophy of Affleck and Leap. Okay. This is basically the same as the twist operator that I considered in the introduction, but here, now the rotation angle is given by this general theta function. Okay, And I first claimed that this U theta is a local operator. It doesn't look like a local operator, but look, if J is in this here less than Jx0, then theta is 0. So this is nothing, the same as identity. And also if J is above x1 somewhere here, then because of this relation, trivial relation, again, this is identical. So it's nothing. So this acts non-trivially only on this interval between x0 and x1. So it's a local operator. And I also recall that in this definition, I still use the convention that 2j and 2j plus 1 form a unit cell like this. Okay. Now, this is an important observation. As I said, this gamma transformation changes n to 1 minus n. So if you apply gamma to this u theta, then this n changes to 1 minus n, 1 minus n. And then I have minus 1. This means that you get plus 1. So 1, 1 minus 1. You get plus 1. This means that gamma u theta is equal to u theta Dagar, okay, Hermitian conjugate. So this means, and recall that the invariance of omega with respect to the transformation gamma means this. So if omega is gamma invariant, then this means that omega u theta is equal to omega u theta Dagar. This means that this expectation value omega u theta is real. This is very, very important. This reality condition is essential for us. Okay, now I'm ready to state my main theorem. This is my main theorem. Let omega be a unique gapped ground state in the infinite set of the infinite system with energy gap delta E, which is strictly positive. And I'm going to give a mathematically precise definition of a unique gap ground state again at the end of the talk. But you can imagine that this is a unique gap ground state in the standard physical sense. And for any theta function satisfying this condition, so I'm going to take L, I will take L very large, and I take gamma very, very small to make this very small in general. But anyway, for any theta function satisfying this inequality, I claim that the expectation value omega u theta is non-zero. And also, its sign is independent of the choice of the theta function, of course, that satisfies this relation. Okay, with this theorem in hand, we can define a Z2 valued index for this infinite volume ground state. How do you do this? Well, it's very simple. I claim that the sign of omega u theta is independent of theta. So I just take any theta satisfying this condition and define index to be 0 if the sign is positive, 1 if the sign is negative. Of course, this is reminiscent of the property of the Zach phase that we already had. So this expectation value corresponds to this expectation value. So when this is positive, Zach phase is new, like this. And if this is negative, Zach phase is 1, like here. Okay. And again, as before, I call this trivial and this non-trivial. Okay, here are two remarks. Number one, well, this is an easy remark. For the two extreme ground state of the SSH model, we recover from this index the value that we computed for the Zach phase. Okay, this is very easy. So this is a strict extension of the Zach phase. And the second remark is a difficult one. As for the class we consider, it is believed that Z2 is the correct classification. And this is based on the very difficult argument based on Bordism and things like that, which I do not understand, but that this is what I learned. Okay, so I'm happy about this. So Z2 is something we expect in this class of models. Okay, so with this theorem, we prove this very important corollary. So for this purpose, I consider a family of Hamiltonians HS within our class, where S runs between 0 and 1 with these two properties. Number one, for each S, HS has a gamma invariant unique gap ground state omega S with energy gap, which is larger than some constant, okay, which does not depend on S. So we have uniformly we have a gap which is lower bounded uniformly. And we also assume that this path is continuous in the sense that for any local operator A, this omega SA is a continuous function of S. Okay, so this is a very standard definition of this connectivity, of the fact that H0 and H1, two models with unique gap ground state, is connected continuously by a path of models with a unique gap ground state. Okay, and people say that HS connected in this way belong to the same phase, same symmetry protected topological phase. Okay, so a corollary of our theorem is that in this situation, the index into omega S is independent of S, the parameter S. So let me prove this, but I only have this space, but this is enough, more than enough. So I fix a theta function satisfying this condition. Then for each S, I apply this theorem. And so theorem says this condition is satisfied. So the theorem implies for each S that omega S u theta, this expectation value is non-zero. Okay. Now, I assume that this omega SA is continuous in A. And now I have fixed theta. So this u theta is just a local operator. So this must be a continuous function. And this takes a real value. This is real and continuous and non-zero. So it's on the real line, continuous, non-zero. So of course the sign can never change, QED. So the corollary has been proved. Okay. And so from this corollary, you easily see that in case if Hamiltonian H0 and H1 have different values of the index, then there must be a phase. They cannot be connected continuously like this. There must be a phase transition. And let me stress that all these arguments make sense only in the infinite chain, because this delta E0 can be as large as possible. It can be very, very large. So no, I'm sorry. This delta E0 can be very, very, very small as you want. So to see this, you have to be in larger and larger system, right? And in order to make this proof, you have to make this guy very, very small. So for this purpose, you have to make this L large and gamma very, very small. Okay. So all this makes sense only in the infinite chain. Actually, this is essentially the only place I must be in the infinite system. Okay. So now we have this corollary and this implication of the corollary. So from this, you see this. This is a slide I have already shown you. So I have shown that I said that H0 SSH and HM1 SSH do not belong to they belong to different symmetry protected topological phases, but this was proved by using this corollary. Okay. So that's the main results, main theorem and its main corollary. So, but let me discuss three other theorems that are proved in my paper. The first one is that something I call the duality theorem, which I think is interesting. So let omega be again a unique gap ground state of the infinite system. Now use this twist operator, which is consistent with the interpretation that 2j and 2j plus 1 form a unit cell, and define this D2 index. Now, of course, for the same ground state, you can use this twist operator. It's almost the same, but this is consistent with the interpretation that 2j minus 1 and 2j form a unit cell like this. So this, by using this twist operator, you can define another index, which I denote by int prime. And then I can prove that if you add these two indices for the same ground state, you get 1. What does this mean? This means, so these are G2 index. So this means that if this index is 1, then this index prime is 0. If this index is 0, index prime is 1. You can have only one of these two cases. So in other words, we have shown that any unique gap ground state is topologically non-trivial, either with respect to this index or index prime. Okay. Here's a small theorem about decoupled system. So this is our class of Hamiltonian. Let H decoupled be a Hamiltonian in this class without any hopping between two half-infinite chains, minus dot 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 minus 2 minus 1 and 0 1 dot dot dot. More precisely, I assume that Tjk is 0 if j and k satisfy this condition or this condition. And then I can prove that if H decoupled has a unique gap ground state, then it must have 0 index. It must be trivial. Okay. So this in particular means that if a ground state is omega is non-trivial, then you can never connect this continuously to omega decoupled. This in some sense means that there is intrinsic entanglement in this non-trivial omega between two sites 0 and minus 1. And you can never cut this. So this is just a trivial, almost trivial SSH ground state. But then here you see entanglement between 0 and minus 1. But this theorem shows that this is true in general. Okay, and this is closely related to the existence of edge mode. And actually I can present this edge mode theorem in several different versions. Here's a clean version, which relies on rather strong assumption. So this is our Hamiltonian, but I further assume that it satisfies translation invariance. So there is an even constant, and both V and T are translation invariant. Okay, and then I denote by H plus the corresponding Hamiltonian on the half-infinite chain, obtained simply by restricting these summations to half-infinite chains like this. Then here's the theorem. Suppose that the ground state omega of H is unique in the global sense. I'm not going to explain. Please look at my paper. Gapped and satisfy and has non-zero index, and topologically non-trivial. Then any gamma invariant ground state omega plus of H plus is accompanied by a particle number preserving gapless excitation near the edge. More precisely, for any given epsilon, positive epsilon, which is small, I can find a local unitary operator U epsilon, which lives near the edge, which when acted on the ground state generates a state which is orthogonal to the ground state and whose excitation energy is less than epsilon. Okay, so there is a gapless excitation near the edge. Again, this is a very simple SSH ground state, and I told you that there is a gapless excitation living here, but this is again generic for topologically non-trivial state. Okay, so in the rest of the lecture, I'm going to explain the proof of the main theorem, but I first explain the theorem in a finite chain. And actually, for most of you, I think this is enough. Okay, so I consider a finite chain with periodic boundary condition, and I want to prove this theorem. Okay, so I take a unique ground state phi ground state ket with a gap delta E. And this is a finite system, so this expectation value is simply this standard expectation value. And I just take a theta function satisfying this. And I claim that there is a very simple and standard estimate due to Bloch and also by Leap, Schultz, and Mattis, which says this. What is this? Well, this is very easy. And I first claim that H and phi ground state are invariant under uniform U1 rotation. Uniform U1 rotation is simply this. This is U1 phase rotation, and this rotation angle theta is a constant. And here we are considering this U's theta. Constant is just a plus minus factor. Here the rotation angle theta j depends on sites. But this theta j changes very slowly, very gradually. So, okay. Now look at here. Here you have state U theta phi ground state. So this is a state obtained by applying this very gradual rotation, U1 rotation, to the ground state. So you expect that this gradual rotation changes the expectation value of H only by a very small factor, actually the theta prime squared times L, the length. And this is precisely this estimate. So look, this is our variational state, U phi ground state. So this is ket, and here you have corresponding bra. So this is the energy expectation value of this variational state. And this inequality says that this energy expectation value is higher than the ground state energy only by a very, very small factor. Actually, this is this. Theta prime is upper bounded by gamma. So this is this. Okay, so this is the standard, very standard estimate, and the proof is very elementary. Okay, so with this and this assumption, we have shown that this is bounded by delta E. Now, you assume that the expectation value of U is 0. You want to show that it's non-zero, so you assume that it's 0. But look, this implies that the inner product of phi ground state and U phi ground state is 0. So U phi ground state is orthogonal to the ground state. It's an excited state, and this tells you that with excitation energy strictly less than delta E. But of course, this contradicts with our assumption. So this means that you can never have this. So we have proved that omega U theta is non-zero. This part has been proved. So we only need to prove that the sign is independent of theta, but it's very simple. Again, continuity argument. We know that this omega U theta is real, and it varies continuously when we modify theta function continuously. And then, of course, the sign cannot change because it's non-zero and real. Okay, QED. Okay, so as I said, if you're not very much interested in infinite system, that's all what I wanted to say. So thank you for watching and goodbye. You can look at the final summary. But anyway, so if you're interested in the infinite system, yeah, let's go on. So proof of the main theorem for the infinite chain. But this is not long. I only have 3 slides. Okay. First of all, so the structure is, of course, exactly the same. I start from this Bloch-Lipschutz lattice type estimate for the variational energy. But now in this infinite volume setting, the energy estimate is written like this. And of course, if you plug in the finite system case, this is exactly the same as the energy estimate that I had before. So here's the proof. Let me go quickly. By using the symmetry, you can rewrite this expectation value like this. And then you see that this is written compactly by using a double commutator like this. And now the interaction part commutes with this U theta. So you find that this is equal to the double commutator of H hopping and U theta. These are H hop and U theta. And now this is just a computation. You do explicit computation and find that this double commutator is written exactly like this. Okay, I know that I'm quick, but this is just very elementary. And then you can norm bound this thing by this. This is norm bounded by 1, and this is bounded like this. And if you recall the definition of gamma, you find this. And then finally, you sum this term, or this term for relevant J and K. And if you recall this summability, you get this. Okay, this is a bit complicated, but very elementary and easy. Now, in order to prove the theorem, I must define what I mean by ground state or gap ground state of the infinite system. Okay, so here are some definitions, quick definitions. By loc, I denote the set of all local operators. By local, I don't mean that it acts on a single site. It can act on arbitrary number of finite sites. That's local operator. Okay, then here's a definition. A state rho is a linear function from this loc to the set of all complex numbers, which satisfies this positivity for any local operator A, and which is normalized like this. And the interpretation is, of course, that rho of A hat is the expectation value of the local operator A in this state rho. Okay, so here's the definition of a ground state. A state omega in this sense is said to be a ground state if this inequality is valid for any local operator B. Okay, here's one remark. H does not belong to loc, because H is defined as a formal infinite sum. But the commutator of H and V is well defined, and it belongs to R log because H Hamiltonian, we only have short-range hopping and short-range interaction. Okay, that was essential here. And of course, in order to compute this, you only need to take a finite volume, finite length ground state in a sufficiently large interval that contains the support of V. Okay, so even though H is not the element of R log, commutator is well defined, and this is an element of R log. Okay, and so, well, that's a formal remark, but what is this weird condition? But this is just a standard notation, standard condition. Okay, so let's look at finite system where omega is just this expectation value. And then this condition is, of course, written like this, if you recall the definition of commutator. And now suppose that phi is a ground state, and choose psi to be this variational state obtained by hitting ground state, the ground state by V and normalizing. And then you easily find that this inequality is nothing but this inequality here, but this is nothing but the variational characterization of a ground state. So you find that this is very standard characterization of a ground state that works in the infinite volume state as well. Okay, so here's a similar definition of a ground state omega, which is unique and gapped. Okay, we say that omega is unique and gapped, and the energy gap is delta E if this inequality is valid for any local operator V, which satisfies this. Again, this is not difficult at all if you consider the same setting. If you choose phi as a ground state, and same setting as this, and then you find that this inequality reads like this, and this condition is simply says that your variational state is orthogonal to the ground state. So of course, this is the standard variational characterization of a unique gapped ground state. Okay, now I can prove the theorem, but it's almost automatic. Okay, so this is the theorem I want to prove. So I first take a theta function with this condition, and this is the lemma that I have already proved. So the lemma says that this is bounded from above like this. And of course, this is just one. This is just one. And now you assume that you want to prove that omega u theta is non-zero, so you assume that omega u theta is 0. But this just contradicts with this definition. Now, of course, you take u theta as b. Then, of course, this contradicts with this. So this means that you cannot assume this. And you have proved that omega u theta is non-zero. And the rest is exactly the same as finite volume case. You only use continuity. So that's the end of the proof. Very simple. I stress that this is a full proof. Nothing has been omitted. Okay. And this is a full proof that works for the infinite volume ground state. Okay, so here's the last slide. This is my summary. So I have presented a rigorous but very elementary index theory that applies to a class of interacting one-dimensional topological insulator, including the famous SSH model. And RZ2 index is defined from the sign of the expectation value of the twist operator. So this makes our theory elementary, the proof elementary. And the index is invariant under continuous modification of unique gap ground state with symmetry. So it's a topological index. And I have also shown that a ground state with non-trivial index has a gapless edge excitation. I don't know, but edge excitation when defined on this half-infinite chain. Okay, so that's all what I wanted to say. Thank you very much for watching, and goodbye.